Hello, my name is Zekun Shen from New York University. Today I'm presenting HeapExpo, a work that prevents use after free vulnerabilities by pinpointing promoted pointers. We studied the CVE database and found the prevailing use after free vulnerability, and the nature of use after free makes it hard to detect. One reason is that use after free involves multiple stages. First, a program allocates a memory, and then it creates copies of the pointer. And after the dynamic memory is deallocated, the copy pointers become dangling. After that, use of the dangling pointers will cause use after free. Although all of the code happened in one place in the example, it could be scattered through the source code. And use after free is likely exploitable if the freed memory could be reclaimed between deallocation and memory access. Prior work mitigates use after free vulnerabilities with an approach called dangling pointer invalidation. This approach treats memory as a graph, where nodes are the dynamic objects and edges are the pointers. It tracks the creation of pointer copies by a specific LLVM store instruction of a pointer type. When releasing a dynamic object, it invalidates all the dangling pointers created by mapping them into empty pages. Therefore, use of the dangling pointers will automatically cause a crash. I just mentioned how pointers in memory are tracked, but tracking registers are hard because register type is ambiguous. We can't tell if it's an integer or a pointer, and the registers are saved to and restored from stack frequently by push and pop instructions. Therefore, there's no such store instruction of pointer type for us to track. Therefore, previous works do not track pointers in registers. But does it matter? From our study of compilers, we know local variables and function arguments are regularly promoted to registers and thus could not be tracked. In LLVM, there's an optimizer called mem2reg that promotes stack locations to registers. For the simple C code, we see the store instruction disappear when we enabled compiler optimization. To study the severity of the problem, we reproduced 19 use after free bugs found by OSS-Fuzz, a continuous fuzzing platform for open source software. We found that 10 out of the 19 bugs could not be tracked by previous work, where 5 of them are local variable pointers and 5 of them are function argument pointers. Our simple solution is to disable compiler optimization with pointers and mark them as volatile. For non-volatile type, a compiler can assume the value of a variable doesn't change unless there's a write to it. Therefore, in the example, the compiler can assume copy 1 and copy 2 are equal and alias them all to the same register. However, if we declare the pointer as volatile, we tell the compiler that the value of the pointer could change at any time. Therefore, the pointer can't make any assumption, and it will not promote the pointer variable to registers. In our design, we have a compiler path that volatilizes vulnerable pointers before all other optimizations. Therefore, at link time, we can instrument pointer tracking code to the vulnerable local pointers. However, it has poor performance because we basically turned off optimization of all the pointers, and it incurs 5 times tracking code as previous work. Therefore, we perform our first optimization based on liveness. We know that a pointer has to be first defined, then become dangling, and after that used to be causing a use after free vulnerability. Therefore, for each function call, we only need to track variables that are defined before and used after the call. In this example, only variable S1 need to be set as volatile because the function call to f lies within its defined use chain. Because only functions that can release memory can invalidate pointers, we have fewer function calls to check. In our algorithm, we recursively check functions for calls to free, and we conservatively think external functions and indirect jumps would call free. In this example, we only need to check function call f and not function call g because f would end up calling free. Our compiler optimization run before all other optimizations at compile time will overestimate unsafe pointers because only calls within a module is visible. Therefore, at link time, we promote safe stack variables so that they can be optimized. In the later slides, we evaluate our work in 4 aspects. We compared our work with Denson, the state-of-the-art dangling pointer invalidation work, to study the effectiveness on use after free detection. We crafted programs that mimic the use after free bugs found by OSS-Fuzz, and we run the code with HeapExpo and Denson protections. We found only HeapExpo could detect use after free with local variables and the function arguments. We also reproduced a real-world QuickJS use after free bug with dangling local variable, and we found only HeapExpo could detect the use after free. In SPEC CPU2006 benchmarks, HeapExpo only has 20% overhead than previous work Denson. And if excluding the 2 propagation-heavy benchmarks, HeapExpo could only have 35% raw overhead. We think the additional protection came with reasonable overhead. Also, in SPEC CPU2006 benchmarks, HeapExpo only incurs 13% more memory overhead than Denson, and it still outperforms the more conventional approach like DenNow. Here we assess the effectiveness of our optimization techniques. Without any optimization, we volatilize all the pointers. We would have 5 times instrumentation as Denson. With optimization turned on at compile time, including the liveness and the call graph analysis, we will only have 2.5 times as Denson. With link time optimization turned on, we promote the safe pointers back. We will only have 1.9 times instrumentation as Denson. Therefore, we conclude that our optimization is very effective on reducing instrumentation. So, in summary, We identified some major false negatives in previous dangling pointer invalidation works. We surveyed use-after-free bugs found by OSS-Fuzz to study the severity. We present a novel approach to address the problem by volatilizing vulnerable pointers. We show that HeapExpo has reasonable overhead given the additional coverages. And now I'm open to questions.